Syzygy episode 81 to Infinity and Beyond, live from the York Festival of Ideas. Welcome to Syzygy Live, which we've titled To Infinity and Beyond. Syzygy Live, why are we calling that? Because it's a podcast, and we would normally record this, and instead we're going out live to the world. I'm looking at the number of participants down the bottom of the screen. It's going up towards 1,000 as I speak. So people joining us from all over the shop. My name is Chris Stewart. I'm not an astronomer. I'm the not astronomer half of the Syzygy podcast, but joining me as usual for our show is Dr. Emily Brunsdon, who is an astronomer at the University of York. Hi, Emily. Welcome to the show.
Hello, and very good evening.
Thank you for joining us. Now, listen, we've got a lot that we are going to be talking about tonight. We're going to be talking about, well, the theme of this year's Festival of Ideas, To Infinity and Beyond, as it applies to the actual universe itself. So we've got a lot to get through because, frankly, there's a lot of universe. But before we do, there's a couple of things that I really should point out, a couple of technical notes. First of all, if you're watching this live, which all of you out there is a little bit redundant, but remember, we're recording this. Other people are going to be listening to it later. So if you're watching this live, you can ask questions. You can actually throw us questions. You don't have to put up your hand. You're not going to butt in. Instead, you're going to go down the bottom of the screen to where it says Q&A, the little Q&A button down there. You can press that one and you can type in your question, and we will gather them all and read through them towards the end and choose out the questions that we think we have a chance of knowing the answers to. We'll see how many we get through towards the end. So please do that. You can throw the questions in there throughout the event. Don't hesitate. Don't hold back. There's no such thing as a stupid question, just potentially a really poorly worded answer from one of us. Secondly, should you have technical issues as we go along, if you lose your way, if you drop out, you can rejoin the event using the original link that came in your invitation email. So just come on back in the same way that you've joined us this time. Please also remember that today's event is being recorded, and so you're going to be able to watch it again if you really want to go back and revisit all the wild and crazy ideas that we've been talking about during today's event. Then you'll be able to watch it again. It's going to be coming up back onto the, we'll be putting it out on our Syzygy podcast, but it's also going to come onto the Festival of Ideas streaming page after the entire festival is over, after about the 20th. Anyway, I'll talk more about that at the end. Lastly, there are subtitles available for this event, and this one intrigues me. I would love to know what it's making of the rambling introduction that I'm doing at the moment. You can turn the subtitles on and off using the CC button down the bottom of your screen, the live transcript button. So you can just press that one and see the mangling of the live speech, but with any luck, it'll help you to read along at home. So listen, that's enough of the technical stuff. This is an astronomy podcast. We like to talk about big things in the universe. And this time around, Emily, we're going to be talking about the actual universe itself. Help me out here. Where are we going today? What's the plan?
So we've got a very, very favorite buzzword I think of today, which is infinite. So I think it's really worth sort of breaking that down a little bit when we talk about the infinite universe. What are we talking about in terms of infinity? But particularly, I guess there's two infinites that are really, really important to look at. And that's going to be infinite space and infinite time.
Yes, infinite space and infinite time. And frankly, there's quite a lot of space, but even a lot doesn't quite measure up to the notion of infinity. Wasn't it Douglas Adams who said, space is big? You might think it's a long way down the road to the chemist, but that's just peanuts to space. Space is indeed very, very big, and it's been around for a really long time. So is it infinite in size? Has it been around for infinitely long periods of time? Is it going to be here for infinitely long periods of time? That's what we're going to try to unpack today. Now, Emily and I were talking about this earlier, and we realized that we could actually talk about this for an infinitely long period of time. So we're not going to do that. We have a limited period to get through tonight. And so what we're going to do is give just a bit of a summary, right? There are a lot of topics that we're going to touch on tonight, which we could spend a lot of time really just delving down into. And instead, we're just sort of going to present some of the ideas and try to put together a picture of our universe as we understand it in 2020-ish. So, Emily, where should we start? Should we start with infinite space or infinite time? Your choice. Which one?
Well, let's spin the wheel. Let's go with infinite space. I think
Okay,
that's a
why
nice
not?
place to
Is that
start.
the easier of the two? I have no idea.
Yeah, I think we're going to bounce back and forth between the two actually a couple of times, but let's
Sure.
start somewhere.
Okay. All right. Infinite space. So this is the question. Is the universe that we live in simply really, 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 really big, like mind-bogglingly big? Or is it actually even bigger than that? Is it infinite? So, Emily, do we have an answer for that?
I'd love to give you a really straightforward, simple yes or no.
Okay, great. Good. Easy. Job done.
I'm not going to do that though.
Oh, that's a shame. Okay.
So I think if we need to actually come all the way back to that question and say, when you say, is the universe infinite or not? I need you to clarify that just a little bit and say, what universe?
Okay. Okay. That to me feels like that should be a really, really easy one to answer. I mean this one, the one that we're in now, as opposed to like what other answer is there to that? I've only got one.
I guess the easy way to start thinking about it is there is something called the observable universe.
Okay.
And this is the bit of the universe that we can see.
That we can observe, hence the name. That makes sense. Okay, so let's start with that then. The observable universe. Like we've been, as a species, looking up into the skies and seeing stuff a long way away for a really long time. So the observable universe, how far can we see? Can we see to infinity? Is that what we see when we look out there into the heavens?
We don't see to infinity, but we can measure the size of the universe that we observe.
Right.
You can put a number on that, and it's something like 93 light years in diameter.
93 light years in diameter.
It's big.
Yeah.
It's pretty big.
Yeah.
So let's remind ourselves that a light year is a really, really long ruler, if you like. It's one of the longest rulers that we use in astronomy. And a light year is the amount of distance. It's not a time. It's very confusing. We're a very confusing bunch in astronomy. It is a distance that is measured by the distance that a photon traveling at the speed of light will travel in a year.
Right. Hence the name light year. It's not a time, it's a distance. And so a light year, I'm guessing, is a really long way. I mean, there are a couple of facts that I have picked up in the previous 80 episodes of this podcast, which is that light travels quite fast, but distances are very large. So the sun is 8 light minutes away.
Exactly.
Right. And Mars is on average roughly what, about the same
months.
Further out?
Well, it's a few light days to get to Mars, depending on where it is in orbit.
Okay.
But I guess a light year is probably easiest to imagine as, but say the distance between our sun and the nearest star is a few light years, three and a bit light years.
Okay, so a light year is of the order of the distance between stars, give or take. Does that seem fair?
Yeah.
Okay. So what was the number you threw around before? How many light years?
It's around 93.
Okay, so that's like 100 stars out, right?
So it's a bit more complicated than that, of course.
Sure.
So when we talk about the distance that light has been traveling, of course, light has been traveling since the beginning of the universe, right?
I can tell this is going to get complicated already. Okay, yes.
Okay, so you would expect that our universe is about 13.7 billion years old.
That's the number that we've currently got on it, right?
Yeah,
we can come to that in a minute, where that number sort of comes from. But yes, let's take as 13.7 billion years old.
Yep.
Yeah.
So you would expect light to have traveled, say, the furthest distance that it could possibly traveled in the universe would be as long as the time has been going in the universe, which would be 13.7 billion years, light years.
That makes sense. That's just simple maths. Yeah.
But then when I say that the universe is actually 93, I think I missed a billion here.
I think you might have. I was getting a bit confused there. Yeah, 93. let's just rewind metaphorically. 93 light years. What you were talking about is 93 billion
light years. That's right.
Okay, so let's just insert that. 93 billion light years, which, like, don't get me wrong, 93 light years is a very long way. 93 billion light years is a lot bigger. Right.
Yeah.
So rewind that and then insert that and then put that one back in again. Let's carry on. 93 billion light years. Now, here's the conundrum, Emily. I'm going to catch you in this one. You ready for it? The universe has been around for 13.7 billion years. You just said that. You also just said that we can see for 90, how many? 90, 98?
93 billion light
93
years.
billion light years. The maths doesn't add up, doesn't work, right? If the universe has only been around for 13.7, then that's as long as light's been going. And you can't do the maths doesn't work. So how does that work? I've got you.
Well, it turns out that the universe hasn't just been sitting there for 13.7 billion years, just doing nothing.
Right.
As we're going to, I think, explore a little bit more on the other flip side of this infinity and the infinite time, the universe has actually been growing. So
Right.
photons can reach us so long as when they started off their journey, they were 13.7 billion light years away from us. But since then, our universe is actually growing. And so now that where that photon was released, let's pretend it was a galaxy that the photon was released from. Then over the time that's passed, that galaxy has moved to a distance, which is now, half of 93, 46-ish billion light years away.
Okay. So because we've got all that time that the light's been traveling, but because the universe has been expanding during all of that time, that the place it actually left from, right out of the farthest distant reaches of where it could possibly have come from, that we could be receiving it now, that's actually a lot further away than those 13.7. Okay, so let's put a pin on that. That's what, about, you said about 47 billion.
Yeah.
Let's call it close. Let's round it up to the nearest 50 billion, right?
Yep.
50 billion light year diameter observable universe. And that's the limit that we can see because light couldn't have traveled from any further than that. Great. Okay, so that's our observable universe. That's pretty big.
Yeah.
There's probably a lot of stuff in that.
There is plenty of stuff to keep us entertained for quite some time.
How many galaxies have you got in the observable universe? How big is this thing? There's quite a few, right?
Yeah, well, we're thinking maybe about 100 billion, maybe plus or minus a couple of 100 billion.
Okay. So the observable universe is a very, very big place. Fine. Let's take it at that. But it's not infinite, Emily. It's of a finite size. It's, let's call it, rounded up to the nearest 100 billion light years across. Very, very big, but very small in comparison to infinity. So is that our answer? Are we just going to stop there and say, no, universe is finite, we're done?
Well, no, because we're more interested in sort of knowing about the entire universe. I mean, universe, the word, it means everything, right?
Everything, right. Even the bits that we can't see.
Yeah, there's an amount of everything that we can see. And you can almost imagine this as being, we live in a bubble, which is our observable universe, our 50 billion light year radius bubble.
Right. And there's nothing special about that bubble other than the fact that that just happens to be the bit that we're in that we can see. But outside of that, we just assume it just keeps on going. Yeah?
Yeah. And we know that it's bigger than our bubble because there's parts of the universe in different times that we've seen that we can no longer observe. So I'm going to come back to that, to sort of put a pin in that. We'll come back to that when we talk about infinite time. But we can see that the universe has been growing and expanding. And we know from our measurements that at the very, very minimum, that the entire universe is at least 23 trillion light years across.
Wait, sorry, hang on. So you haven't left your end of that number off. 23 trillion light years. That's significantly bigger than 100 billion. How do we know? How do we know that it's at least that big? Where does that come from?
Well, it turns out you can do some really nice things by looking at the very early universe. We've got a fingerprint from the very, very early universe called the cosmic microwave background. That sort of is a bit of an afterglow that came not too long after the Big Bang, and it told us some really important things about what the universe was like a very long time ago. So we've got some information from that. And you can also kind of play fast forward and rewind with your cosmological model. So you can build a universe, push play, and sort of see what happens in your models, and then see how big, if the universe was big at this time, we know how much it's growing, then we can see what happens at sometime later.
Okay, so you can play with the maths and the physics and the astrophysics and the cosmology of all of this and say, if we see what we see now, what would it have to have been way back when? And you can create the models and figure out where it goes. Okay, so I can understand that. So let's take for granted And by the way, when I say I can understand that, I don't, right? If anyone's listening at home going, what, you can't understand. No, I don't. I don't understand that, but I'm prepared to pick it up and run with it. So let's assume that the observable universe is 100, what did we say? 100 billion light years across. Okay, I'm going to lose track of these numbers in a minute. 100 billion light years across. And you said a minute ago that there's more than we can, beyond where we can see. There's a lot of stuff we can't see. And it's up in the, how many trillions?
About 23 trillion, maybe.
23 trillion light years across. But you said at least. So that implies that there's sort of a kind of a lower limit there. So where does that come from? Like, is it much bigger than that? Is it infinite? Is this
well? This is actually the surprisingly easy question to answer, because what you're now effectively asking. Yeah, it's easy.
Glad we got there eventually.
You're basically just saying, okay, is the universe infinite or finite? So is it infinite? Does it go on forever, or does it have a particular size?
Like, we can throw around really, really big numbers like trillions and trillions and trillions of light years, but ultimately when it comes down to it, any finite number is really small in comparison to infinity. So what we're really trying to get at here, Emily, is it infinite or not?
We don't know.
Come on. All right. Throw me a bone here. All right. You did say at least that number of trillions of light years. So what do we know? We must have something.
Well, that's pretty much it. We know the lower limit of how big the universe is. We have no idea what the upper limit, if there even is a limit, might be.
Right. So it might be infinite, but if it is finite, it's at least a lot bigger than we see now. Right. Can you give any kind of indication as to, like, why do we put that lower limit on it? Like, we can see the bit that we can see. So how do you then make that next step out to the bit that we can't see must be at least this big? Where does that come from?
Yeah, as that comes from our measurements going from all the way back to the most distant galaxies that we can see, which we knew when the light was emitted, they were in our observable universe. Mm-hmm. But now, since the universe has expanded in the time it's taken for the light to go from that galaxy to us, that galaxy is no longer going to be in our universe. So basically you get this kind of edge of the observable universe where galaxies, as time goes on, moving beyond this edge.
They fall off. They fall off
the edge of our observable universe. Thankfully, they're still in the universe. It's fine. They're fine. The people in those galaxies are all fine. Nothing's happened to them.
We just can't see them.
We just can't see them anymore.
Right. Okay. So let's just recap quickly. Is the universe finite or infinite in spatial extent, right? In size, in physical spatial size? And the answer is don't know. It might be, but if it's not, it's at least a heck of a lot bigger than we can actually see, right? So we can see a lot, but there's a heck of a lot more that we can't see. We know that much, and it could actually be infinite. So wrap your head around that one. That's a bit nuts. So
it's not even clear whether we have the ability, not just kind of with our technology, but even in the laws of physics, to actually find out if the universe is infinite or not.
Isn't that like that just does my head in, that you get a little bit blasé as you read about this stuff, when I talk to you in this podcast, Emily, about what we know about the universe. And when you consider, like, only 100 years ago, we learned that there were other galaxies, right? It's only a century ago that we learned that the Milky Way galaxy that we're in is just but one of many, 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 many galaxies in the universe. And our galaxy contains billions of stars, and we're just one tiny little dot in this. Like, we only learned that 100 years ago. And then since then, people have been developing their ideas and coming up with equations and models and ways of winding back the clock. We'll talk about the clock in a second. We haven't even started on the clock. To the beginning of the universe itself, and then playing that forward and expanding the universe out and coming up with answers like, we live in a universe which is 13.7 billion years old and which is 100 billion light years across, and is part of something which is at least in the many trillions, if not infinite in size. Like, that is like, well done astronomers, well done cosmologists, big round of applause from everyone. So that then leads us to the next question. How old is the universe, and will it go on forever? The infinite time question. So, Emily, where are we going to start on that?
Yeah, now this is getting exciting too, because again, we've got some answers. Some of these questions are sort of the easy ones. Let's not play down the fact that cosmology has taken an awful lot of time, effort, blood, sweat, and tears to get to this point. But we do have some fairly good answers to some of these parts of this question. But some of them are kind of it's fun because there are some open opportunities to explore as well. Let's start with how old is the universe?
Okay.
So we keep bumping around this 13.6, 13.7. It's kind of
that you just casually threw out there a little while
billion
ago.
years.
So, by the way, we know that. Really? Okay. The universe is that old? How?
Well, we've got very, very handily this thing called the cosmic microwave background, which is the afterglow from the Big Bang. It's the first time that photons were able to freely roam around the universe after the Big Bang. So we've got this really nice measurement from that. We've got some other really nice measurements that take us back to if the expansion is happening the way it's happening now, then if you push rewind, then you can get everything back to collapse back down to the Big Bang. All of these kind of measurements that we're making about the universe are all convalescing, if you like, or coalescing. That's a better word.
Let's go with that one. Yep.
Coalescing into a single point of an answer, which is giving us this 13.7 billion years.
So is it as simple, just to clarify that, is it as simple as we are seeing evidence right now that the universe is expanding? Things, the whole notion of the further you look out in space, the more things seem to be moving away from us, right? And that was either going to be, well, we must be the center of the universe and everyone's running away, and that seems unlikely, or you'd see the same thing if the universe were expanding, right? And so that was, when was that sort of figured out? That was about 100 years ago.
That's Hubble's law. Yeah.
Okay. So the universe is expanding. The further away you go, you see distant galaxies receding from us. And that's what you'd see if all of the space between were expanding. Is it as simple as you then take that idea and roll it backwards, run the film backwards, and things come closer and closer and closer and closer. And you keep doing that. You run it backwards and ask yourself, how long ago was it all sitting on top of us? Is it as simple as that?
You can, yeah. And you get a pretty good answer actually from doing that. There are subtleties to this kind of calculation. It's not just kind of like go straight backwards. You do have to add in a few other little bits of physics along the way. But broadly, yeah, you can actually do it.
Right. So with those subtleties, winding that videotape back, you get to 13.7, 13.8 billion years ago. There was this cataclysmic kaboom called the Big Bang. And that's when the stopwatch started. That's the beginning. That's when time started.
And then from there, let me try and give you kind of the history of the universe up until now in about 20 seconds.
Okay, go for it. Start.
We've got some limited time. So then you've got the universe happens. You get this from some kind of singularity, perhaps some kind of quantum fluctuations. Not exactly sure, but it happened.
Gloss over that bit. Push it under the carpet.
Lots of particle physics, exciting atomic physics happened. Then we had the cosmic microwave background, which was the release of photons to freely roam around the universe. That happened when the universe was about 370,000 years old. So pretty young.
So you just glossed over the first 370,000 years of the universe, which, on a human time scale, that's a really long time. On a cosmological time scale, it's not very much.
Not very much at all.
A little bit.
We then went into something called the Dark Ages, where we were waiting for the first stars to be born. The first stars started to come along maybe 150 million years into the universe's age. And then maybe the first galaxies started to come around maybe 300 million years. These are quite optimistic numbers. You can just sort of play with those figures a little bit. And then if you wait another 100 million years, then you get to the point of the first galaxy that we can see formed. So the oldest galaxy that we can see probably formed maybe something about 400 million years into the universe's history.
Okay.
Our galaxy, however, took about something like 5 billion years to form. And then if you come down to our sun, then our sun took something like 9.2 billion years to form.
Right. 9.2 billion out of 13.8 billion. So we're actually fairly late in the grand scheme of things.
Yeah, we're not the first generation of stars by any means.
Right. How many, roughly speaking, how many generations would we have gone through?
We talk loosely about 3, but it's probably not really exactly 3.
Right. But it's not hundreds. and it's not two. We're several generations in of stars sort of being born, going through their lives, exploding or burning out, doing what they do, and we go through another cycle of that. So we're several cycles in, which, you know, in and of itself, like, that's kind of interesting. It to me feels like a universe which is it doesn't feel ancient. Is that a strange thing to say, that 13.8 billion years suddenly seems like not such a really long period of time? If you'd said that our sun is like a 400 millionth generation star, then it's like, wow, that's a really long time. Like, you know, the universe has been around for a really long time. But if you said, no, we're just sort of, you know, maybe third generation, like, it's not a lot.
The numbers do feel quite friendly in time. They do feel friendly.
Yeah.
Well, for now.
Good, right? You're just softening us up, are you? Okay,
of course.
So was the easy part, was it?
Yeah, that's the bit that we can actually get reasonable amount of data on and understand.
Okay, all right. So that gives us a finite time in the past. The universe has been around for a finite time in the past since this roiling cataclysmic explosion, which we call the Big Bang. We are now in the present, 13.8 billion years later. So is the universe going to keep going forever? Is it an infinite future that we see ahead of us?
Well, this is a great time to actually segue a little bit back to our infinite space topic. Right. Because it turns out the answer to that question depends on what shape is the universe.
What shape is the universe? Okay. Talk me through that one, because universes have shapes. What kind of shapes are we talking about?
They definitely have shapes. And this is going to be horrible because it's unfortunate that we cannot imagine the number of dimensions that the universe actually sits in. But we're going to give this a real good go and sort of to describe the possibilities of the shapes of the universe.
Okay. So we're putting a warning on this one, which is A, this might break your brain because it's sure as heck going to break mine. And secondly, you know what? Podcasting is an audio medium, and this is hard enough to show in pictures, because what we're trying to do is describe a three-dimensional or even four-dimensional universe, often on two dimensions, and in our case, in no dimensions. We're painting word pictures here. So Emily, good luck. Godspeed. Talk us through this one. What does it mean to say the universe has a shape?
Well, what we're saying with shape is we're talking about the geometry of space-time. Now, space-time is kind of the underlying way that we measure the shape of the universe. So if you had a piece of paper that you had a graph on, a grid, say some maths paper where you had nice little squares, you would say that your geometry is in two dimensions there because you've got kind of an X and a Y.
Sure. Going that way, going that way. Got it.
Yep. And then we obviously work in three dimensions. I mean, we're two dimension in Zoom, but if we were face to face, then we'd have some extra dimension in the Z axis. And then time is our sort of fourth dimension in general geometry of space time.
Sure. Easy so far. I'm with you.
Cool. Now, it turns out if you want to describe different shapes of the universe, we're actually going to talk about them in two dimensions, and you have to blow up your brain to try and imagine the analogy of what that might look like in three.
Yeah, and that's different to imagining a two-dimensional thing like a sheet of paper in our three-dimensional space. We're asking you to imagine the equivalent of a three-dimensional sheet of paper. So, okay, let's go from there.
Yeah, yep. The problem is we're trying to describe a universe that we are inside of. Yeah. So we can't construct a model of something that's outside the universe because it would be more universe.
Yeah, that doesn't work. So caution to the wind. Let's do it anyway. Talk to us about universal shapes.
Okay, so I guess the straightforward one is the universe could be flat.
Right. That seems to me that would be an easy one. Yeah.
Yep. That's your sheet of paper. You can have, your sheet of paper that goes on forever. It can be infinite, or you can have ways where your sheet of paper can be finite. You can even have ways that your sheet of paper wraps around on itself. And if you go for long enough in one particular direction, you end up where you started.
Okay.
So there's different ways to construct a flat universe. But
in that sense, when you imagine a sheet of paper wrapping around on itself, you make a tube which you could look through. That's not you're not allowed to look at it that way, but it is that way in the sense that if you go around that tube, you come back to where you started from, right? That's still flat.
Yes.
Right. Yep. Okay. Right. Staying with you. I'm hanging on by my fingertips. Yep.
So that's our flat universe. And I guess in some ways it's the most mathematically simple way that you can construct a universe.
Yeah. Straight lines. Easy.
Now, you have two ways that you can then curve your universe to create
Mhm.
two alternative shapes. You can curve it, first of all, you can curve it closed. So this would be take your sheet of paper and turn it into a ball, a sphere.
Right. Yep. And this is again a little bit different to wrapping a piece of paper around in a tube and looking. This is we're now trying to imagine a three-dimensional space wrapping around in a sphere in four dimensions. It's very, very difficult. But what would that mean? What would that mean if our space were curved that way?
It would mean that a universe is definitely finite. That's the
Right.
one. That's the only place you can exclude infinite universes is if you decide that if you discover that the universe is closed in this curvature.
So what would that look like? What would we like? Let's assume that the universe isn't really big. Let's assume that the universe is small enough that we could actually observe what's going on. What would a closed spherical universe look like? Would it mean looking up into the sky and seeing the back of your own head? Is it that kind of idea?
Essentially, yes. Yeah, you could look in two different directions and see the same galaxy because the light could come from the front of the galaxy or the back of the galaxy.
Oh, right. Okay, because you do the same thing if you imagine on the surface of a sphere, right? You could look east west or you could look north south, and you'd come around on yourself, back on yourself eventually anyway. Either way, so it's curved in that sense, right? Okay.
Yeah, so we've done quite a lot of measurements
way.
for that one, and we've not been able to see any hint that the universe is the same in any two directions in the sky.
Right.
So it's probably the least likely.
Okay. So I mean, it could be that. It could just be extraordinarily large.
Yes, yeah, just very big, but it would have to be finite for that to happen. Yeah.
Okay. All right. So that's one way.
And the other way you can curve your universe, which is our third shape of the universe, is you can have it curved but open. Now, this one's a bit of a weird one to imagine. I think the way I imagine it is you take a saddle from like a horse.
Mm-hmm.
And when you take a saddle, imagine it's like a real big cowboy saddle where you've got this big, deep curvature. Then it comes up at each end in front of you and behind you.
Yeah.
But then your legs go down.
Okay, so it's curved one way in one direction and it's curved the other way. I'm doing hand motions at the moment, like that helps anyone listening to this, but there we are. It curves one way in one direction, curves the other way in the other direction. It makes a saddle shape, which is different from a sphere. Okay,
yeah. And it's infinite open. In both of those directions.
Right, because it doesn't bend around on itself.
No.
Yeah, you can't keep going in one of those directions and come back on yourself. Both of them keep going. Okay, cool. So that's open, infinite, but still that's still curved, but in that case it's open and infinite. All right.
Exactly. So those are our three potential shapes of the universe. Turns out it's pretty hard to measure what our actual universe is when you're stuck inside of it. Right. Particularly when you're stuck in a bubble, which is only a fraction of the entire universe.
Yeah, I mean, it's starting to feel like our observable universe is actually a bit too small. Frankly, I think, whoever was working that one out just got it a bit wrong. We needed access to more of space to figure out how big space is. So we can't see any evidence for curvature. Is that what you're saying?
We're trying really hard, but so far we can't actually say exactly whether the universe is curved or not. So far, all our measurements point to it being flat, but there is an uncertainty where it could be a little bit curved.
Right. I know this is an entire podcast episode in itself, but how do you measure how curved it is? What are you looking for?
Well, we're looking for really, I guess, one of the best ways to imagine it is how much mass there is in the universe, because this will also tell you what the future is going to be. And when I talk about mass, I'm talking about all the mass. I'm talking about the mass that we see. I'm talking about the mass that we don't see as well. Now, if that mass has enough density, that means that the gravitational pull of this mass is strong enough to overcome the current expansion, then you're going to see the universe kind of going out, expanding, and then that mass is actually gravity is going to take over. The universe will sort of come up to a point, stop, turn around, and then come back again. So that's another way to imagine your closure of the universe.
Okay, so it depends on how much stuff there is in the universe, which is all gravitationally attracting each other, right? We're going around the sun because of the force of gravity between the sun and us, and that's sort of keeping us in check. And so if you're saying if there's enough stuff in the universe, then we're expanding now, but eventually that force of attraction of the gravity would dominate and everyone would slow down and then come back together again. And what big crunch is that the future under
Yeah,
that
so
scenario?
this is outcome number one for the infinite sort of end of the universe. You can have your big crunch, and things can crunch all the way back down. So it's almost like having the Big Bang in reverse. So Big Bang, universe expanded, and then big crunch, everything comes back together.
Right. Okay. That doesn't sound fun. We came out of an extraordinarily violent explosion. Going back to an extraordinarily violent explosion doesn't sound like a barrel of laughs. So let's say, for the sake of an argument, that is our future. How far away would that be?
Well, it depends on how much
about?
Mass you have. If you've got lots of mass, then it happens quicker because gravity is stronger. If you've less, then gravity is weaker and it takes longer. We don't have any numbers on that because that's actually turns out to be the least likely current scenario.
Oh, okay. Well, currently, that's good.
We don't see a way that could happen.
So future death by cosmic implosion seems unlikely. That's, tick that one off. That's a positive. That's a positive for 2021, folks. There we are. So that one we count out. So what are our other options then?
So the other one, I guess, is when you've got the open universe. So this is curved, but curved the other way. So things are sort of in that weird saddle shape. Now, this is what's happened when basically there's two options with this one. I'm going to talk about the extreme option. This is where the universe is expanding and the rate of expansion is getting faster and faster and faster, and it's just pushing itself totally apart. This is the extreme scenario, right?
Right.
We call this one the big rip.
So if you're not going to have a big crunch, you might have a big rip. So is this where the universe tears itself apart? Is that what you're telling me?
Exactly. Yeah. So currently we're in the position where things are being pushed apart. Galaxies are moving further and further apart from one another with the expansion of the universe. But if that force of pushing gets stronger, then galaxies, the stars in the galaxies, are no longer going to be gravitationally bound to each other. So the stars are going to start to come apart in galaxies. The planets that are going around stars are going to be pushed away from their stars. The material, the atoms that make up planets are going to be pushed apart. All the rocks are going to be pushed apart and all into their individual atoms. The people, if they're still there, are going to start to be pushed apart as atoms break apart.
This is not comforting at all, Emily. What are you doing?
Oh, it's not really that fun, is it?
It's not. So put me out of my misery then. Is that like how far in the future would that be?
I think basically the quickest you could possibly do it based on our current measurements is in about 22 billion years.
Okay. So given that the universe has been around for 13.8 billion years, we've got that plus a bit extra to go for that worst case scenario. That's a bit more comforting. I think that's okay. That's not too bad. But is that what we think is going to happen? Are we approaching a big rip?
Pretty unlikely. Currently, looking at the current rate of expansion of the universe, doesn't look like it's quite strong enough to do that.
Right. So we're sort of sitting in this middle ground where it's not the big crunch, it's not the big rip. So it's the big what? The big nothing.
Big flat, I guess.
Flat. So what's that future look like?
Well, so in a flat universe, or even in a very slightly curved universe, but not super curved, then what happens is you just keep playing with time. And this is where we go through the evolutionary history of the universe as it's played out so far. So we've come from a place where stars were born, stars have died, new stars have been born, new stars have died. But all in that process, you've always created objects that do not therefore further contribute to the universe. So you end up with these kind of just dead lumps of mass. You end up with black holes that are kind of just dead lumps. Black holes very slowly evaporate, but it takes a very long time.
Right. Okay.
Effectively, you end up running out of energy in the universe.
Right. Everything just sort of slowly but surely cools and dissipates and goes dark.
Eventually, it comes into what we call thermodynamic equilibrium, which is basically where, say, you got your hot cup of tea and you take it into your office. Yeah. Eventually, that hot cup of tea becomes the same temperature as your office, right? It returns to some thermodynamic equilibrium.
Right. And so that doesn't sound like a particularly interesting future universe where everything's basically smeared out into one vaguely lukewarmish cup of coffee. That's pretty unpleasant. So under those circumstances, that just keeps going on like that forever. So that's
Yeah.
that's infinite time with
A little
not a
bit.
lot going on.
We do have a little bit of a boundary. We do think, based on our measurements, what we can see with the mass and the energy that we have in the universe around us, there is a point where that thermodynamic equilibrium will be met. Now, this is going to be a good one for you. You're going to really love this one, Chris.
Am I though? Am I?
The time it's going to take to get to this point.
Yeah. Okay.
And I know you like big numbers, but I think this might be the biggest number we've ever talked about in this podcast.
Right. Okay, hang on. Let me get a grip on this. 13.8 billion years ago, the universe began. If the big crunch was going to happen, or the big
death.
the big rip, no, because we were talking a minute ago about the big rip,
yep.
And you said that the soonest that might happen was about in the 20-somethings of billions of years in the future. Those are very big numbers already. So I'm just stealing myself now.
Okay.
How far in the future are we reaching thermodynamic heat death of the universe?
So we will definitely die.
Yeah.
First, before we reach there. So we will definitely die in 10 to the 14 years.
10 to the 14. That's a 1 and 14 zeros years into the future. So just to be clear, right, a billion is 10 to the 9. So we were talking about 20 billions into the future for the big rip. So that's 20 with 9 zeros after it. This is 14 zeros, a 1 with 14 zeros. That's a lot. That's a very, very, very long time, Emily.
We'll definitely die because there'll be no more stars after that point.
Right. Okay.
There will still be universe for a little while, though.
For a little while.
For a little while. Well, here's your number. from the point when stars stop.
Yeah.
Well, from now until the absolute end, the thermodynamic equilibrium, the ultimate heat death of the universe, is 10 to the power of 1,000 years from now.
1 with 1,000 zeros after it. And what happens at that point? That's when it's all just, everything's just stopped. There's going to be no more change. That's just it. It's just this one big gray wash of nothing.
That's it.
In the universe. Well, you know what? I'm going to take a little bit of comfort from that to know that that's a really, really long time. But then presumably that would just sit that way forever. So it's not a particularly interesting future, but it is an infinite one. So can we take some solace from the possibility that at least we've answered one question tonight, which is that the universe might last forever? Can we do that?
I would say yes. I'm just going to throw you one last little curveball in there.
Okay. All right.
Are you ready?
Yep. Hit me.
All of the things we've talked about are based on the universe as we observe it now.
Sure.
In the universe, we have things like stars, galaxies, matter that we understand, you and me.
Yep.
We've also got this thing called dark matter. It's a thing. It's there. It's just more matter. It doesn't really matter in this context, but it's there.
We don't know what it is, but it's there. We can see it. We can see that it's there. Yeah.
We've got something else that we don't really understand, though.
Mm-hmm. And that's what?
Well, it unfortunately could change any of these three scenarios depending on what it does.
Right. And this is what?
And that is dark energy.
Right. So we've got dark matter. That's not sufficient. We've got dark energy. And that's what then? We don't know.
It's basically the thing that's pushing everything apart right now.
Right. Okay.
We don't know what dark energy is. And we don't know where it came from. We know that it kind of started to take over and turn on about 5 billion years ago.
5 billion. So only, let's call it a third of the age of the universe. It started to become important ago.
But we don't know why.
So we don't know what it is. We don't know why it's doing what it's doing. But at the moment, what's the big deal? Why do we...
If dark energy gets stronger, then it's going to push us into a big rip because it's pushing things apart faster. So it's going to push into a big rip.
Okay.
If dark energy turns off, then we're going to end up with a big crunch because there'd be nothing pushing the galaxies, etc., apart anymore. So we're just going to collapse back down.
And given that in the past it's done something weird by actually becoming a big thing in the universe, it could equally not in the future, or more so, or capricious dark energy. So under those circumstances, then, with our current best estimate, I'm going to just pose the question one last time before we finish up tonight, Emily. We've already put a big question mark, dunno, on is the universe infinite in size? Is the universe going to last forever? Answer, please.
Not the foggiest.
Right. You heard it here first, folks. Well done. Well done, everyone. Oh, dearie me. Look, I think we probably need to wrap up this increasingly ludicrous conversation about the size and scope of the universe, because we've got a couple of questions that have been coming through. If you out there in listener land, listening to us live, of course, if you're listening on the podcast, there is no way that you can send us a question that we can answer now, because time doesn't work that way. But if you are listening at home right now as I'm speaking, then you can send us a question via the Q&A button down the bottom of the Zoom. We've already had a couple through. So, Emily, is it all right if I just throw a couple of these at you?
Absolutely. Let's go for it.
All right. So, first one that came in from a listener at home called Bruno says, what is cosmic inflation, and does this change the age of the universe? Now, I think this was part of the original discussion about the size and the 13.8 billion that we kind of just sort of shoved under the carpet there. But the whole cosmic inflation thing, can we just, in 15 words or less, Emily, what's that then?
So going back to our timeline of the universe, cosmic inflation happened in the very, very early part and within the first second. Basically, the universe was very, very tiny. It became very, very big, very, very quickly and inflated. We have some idea of why, but not really a full picture. We're trying to still figure that one out.
To be fair, these are really difficult questions, right?
They are, yeah. It doesn't really change the age of the universe because we see the after effect of the inflationary period in the cosmic microwave background. So we know what happened after inflation.
Yeah.
Whether it still has some extra tiny effects going forward from that, maybe subtlety. But when you're talking about an error bar of maybe 0.1 billion years, you've got a little bit of wiggle room to absorb those complexities.
I am just going to throw in here, listeners at home, and in particular Bruno who asked the question, go and search out. There's a blog by an astrophysicist by the name of Ethan Segal. Is that his name? The blog is Starts with a Bang, which is a great name for a blog about the universe, in which he talks about inflation and the tantalizing possibility that if you consider that the Big Bang was basically when it just went kaboom, which was basically at the end of the inflationary period, then there's one way that you could say that the inflation may have been going on forever before that. So go and have a read. I'm not going to talk any more about that because I'm not qualified to do so, but it's intriguing nonetheless. Let's go on to another question. But we didn't really answer that question. Does that change the age of the universe? Your answer to that was not really, at least as we define the Big Bang in the way that we define the Big Bang. Here's a question. How do we measure the age of the universe if time changes near massive objects? This is the whole Einstein thing, which says that if you've got something really, really massive, then that bends your brain as well as space and time. It warps space-time around it, and anyone who's watched the movie Interstellar knows that that does weird things with time. So if all of that's going on, how do we even measure the age of the universe? How does that work?
Well, luckily, all of this stuff comes from basically the same place. This all comes from general relativity, Einstein's theory of general relativity. And so when we build our models of the universe, actually, hey, it was Einstein who came up with the foundations for these models. They've been refined and added on since then. But it is actually Einstein's four-dimensional space-time. It's Einstein's theory of general relativity that sits underneath all this. So
it's basically got it baked in from the start.
It does, yeah, right. Which is
nice.
Well,
that's nice to know. Well, that was a question from Elijah, so thank you, Elijah. Moving along, we've got anonymous attendee is asking, is there a way, and they're allowing us current knowledge of the laws of physics, ignoring technological boundaries, et cetera, et cetera, et cetera. So is there a way that we know of now that we could slow down the entropy and delay heat death? Because frankly, Emily, a 10 or 1 with like 1,000 zeros after it is apparently not long enough. Can we delay that with any technology that we have at the moment? I'm guessing the answer to that is no.
I'm going to quote for you basically the only Simpsons quote, which I know.
Yeah, go on.
It's when Homer Simpson says to Lisa, "In this house, we obey the second law of thermodynamics."
Fair enough. So we might be able to do something on a very local scale, which is exactly what we do. We make order out of disorder. But the universe itself is just going to keep on keeping on. It's going to keep marching towards that heat death in a very, very long time. So, anonymous attendee, I don't think we really need to worry. Alexandra has asked, if when the universe ends via, look, take your pick, any of these three methods, would it just explode and start all over again? Is this a cycle? Like, what happens?
It's a good question, actually, because it turns out that you can turn any of these three universes into a cyclic universe sort of scenario if you want to.
I do. Who wouldn't? Who wouldn't want that, Emily?
It's interesting because so in the Big Crunch, it's pretty obvious that you crunch back down. It looks like a Big Bang, and you can start all over again, and you can kind of get this bouncing universe sort of scenario.
It sounds
crunch bang,
plausible.
crunch bang, crunch bang. Fine. Then in either or both of the heat death or the Big Rip, it turns out there are some theories. Now I'm going to say some of them are a little bit out there, but to do with things like quantum fluctuations, where you can randomly reorganize the universe into a place where it can effectively rejoin into a singularity and start again. It's kind of like an anti-singularity, though. So it's kind of like the opposite of a Big Bang, where everything was together. It sort of just starts off, but in the opposite way.
I hear you speaking, and like, did you ever see any of the TV shows or the movies which involved Snoopy and Charlie Brown, and all the adults just going walk, 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 walk? That's what I'm hearing at the moment. Just quantum fluctuations and like the opposite of a singularity. But let's take your word for it. Sure, we could start all this
maybe.
over again.
And if you believe in vacuum energy, then there's a way to do it as well. But yeah, It's possible. But all of these are mathematical constructs rather than anything that we've got any hard observations of.
I mean, this is the thing, right? Is that cosmology is a bit of a mathematical playground because we don't have all of the answers to this yet. Then it's a way for physicists to be able to play with ideas and go, well, what if it was like this? And what are the consequences of that? And could we see any sign of that in the universe as we see it? It's a lot of fun. Okay, so that was from Alexandra. Thank you, Alexandra. Sarah has asked, what was there before the start of the universe? Perennial question. Anytime you're faced with the universe began 13.8 billion years ago as a very, very small thing, which had a lot of heat and stuff, and Big Bang. Yeah, but what was there before that? So, Emily, what do you got?
I guess there's two ways to answer this question.
Yep.
The first way is no idea.
That seems like an honest answer, sure.
And I guess mathematically and in cosmology, there's no real way of knowing, because if there was anything before the singularity point of start of the universe, in the current way we construct cosmology, it can't have had any impact on how our universe has evolved since then. So anything could have happened, but it had no impact on our current time in the universe. The other way to answer it, which is maybe a little bit more boring, is time didn't exist before the start of the universe. So there's no point in asking what happened before time existed, because that time didn't exist.
That does seem a bit of a weasel out of it, doesn't it? So, well, time actually began with the universe. So your question doesn't even make sense. I just think that's ultimately not very satisfying. Yeah.
It's not satisfying, but it's true in the same way that even
it's not satisfying, but it's true. Yeah.
Even if you have something very, very large, it's expanding. It's not expanding into something because it itself is expanding, because it's the universe.
What you're saying is
one of these fun things.
It's complicated. It's
yeah.
This is the fun part of all of this stuff. You think you figured it out, and then you realize no, you haven't, and you've got to go back and start all over again. Thank you, Sarah, for that question. I'm going to move on to the next person who's thrown in one that we haven't had one from yet. Isabel says, how, Emily, how can the universe have expanded to an infinite size if it started from a point in only 13.7 billion years? And I'm going to say, yep, the maths doesn't check out. If you divide a point by 13.7 years or multiply, or either way, you don't get infinity. So
yeah, turns out that point wasn't a point. Okay, so we haven't gone from a size to an infinite size.
Right.
So we didn't have a size when the universe started. It didn't have a finite size. It was always infinite.
If it's infinite.
If it's infinite, it's always infinite. You can't start finite and go infinite. You can't start infinite and go finite. You have to be
go through a
consistent,
teenage period of becoming infinite and grumpy, and it was always infinite. So what even do we mean when we say a Big Bang then? Because we talk about it becoming really small and squashed up, Emily. How can it be infinite and small and squashed up?
Okay, I'm gonna have a real fun with this, and you're gonna really not enjoy this bit.
No.
All right, it turns
I'm blaming
out,
you, listeners. This is your fault.
Turns out when you have infinites, there are different sizes of infinites.
Oh, don't do this. Don't do this to me. different kinds of infinite, right?
Some infinites are bigger than other infinites.
Right, okay.
I can give you an example.
Go ahead. Yep.
Okay. If you start counting numbers,
Yep.
counting numbers 1, 2, 3, 4, 5, etc., right? You know that there are an infinite set of numbers. You can
Yes.
keep adding numbers
do.
and you can go on forever.
Yep.
It's infinite set of numbers. There are, therefore, an infinite set of numbers which are multiples of 10, because there's 10, 20, 30, 40, etc., etc., etc. They go on and on and on. There are also infinite number of numbers which are just integers, 1, 2, 3, 4, 5.
Yes.
But we can agree that the infinite number of integer numbers is bigger than the infinite number of tens.
No. What? They're but because there's 10 integers for every 10, so that infinity is 10 times bigger than the other one.
It's a bigger infinite.
All right, ladies and gentlemen, we are going to have to wrap this up. So if a potentially infinitely sized universe hasn't satisfied your lust for infinity, if a potentially infinitely long-lasting universe isn't enough for you, if different kinds of infinity isn't enough for you, then I don't know what more we can do for you. But we're just going to have to leave it there with, it could be infinite, it might not be infinite, but it's really big. Either way you look at it. We have been the Syzygy Podcast. My name is Chris Stewart. This has been Dr. Emily Brunsdon, who is an astronomer from the University of York. She's actually at the Astro Campus at the University of York. And coming up at the Astro Campus in a couple of days' time, there is going to be a viewing of the solar eclipse. You can't go there in person, but you can tune in live on the interwebs. We are putting some links into the chat right now of a couple of links that you can go to go and watch that solar eclipse live. That's coming up when, Emily?
On Thursday morning.
Thursday morning. A couple of other things that are coming up. The festival, of course, continues on. Emily is going to be hosting one of the events where an author whose name has just escaped me.
Emma Chapman.
Emma Chapman, and she is going to be talking about her book. Emily is going to be talking to her about her book. Emily, talk to me about this one. What's happening?
It's all about the first stars. So if you're interested in that part of the universe when the first stars came about, then come along and hear her talk about her research in that.
Excellent. And I am going to be hosting an event involving our mutual good friend James Lees, who's a PhD student at the university in physics and also a bit of a science nutter. And he's going to be talking about, basically the title of his talk is You're Stupid and So Am I. It's a personal insult, basically. Talking about the way our brains fool us and the things that we tend to believe when we don't think hard enough. So have a look out for both of those. We've got links in the chat. But now we've come around to the turn of the hour, so we're going to have to come to an end there. Really sorry that we didn't get through all of the fabulous questions that came up in the Q&A, but thank you for joining us, all the several thousand of you who ultimately participated in this show. If you want to catch more of our podcast, Emily and I do this fairly regularly, every week or so. You can find us at syzygy.fm or point your podcast player of choice in the direction of the Syzygy Podcast, and you'll find it. This has been episode 81 of Syzygy. We'll be back again in a week or so's time with another regular episode. But otherwise, thanks so much for joining us for a live episode. This one is going to be put live up on the website. Recording is going to be available on the festival YouTube channel, which can be accessed from the Watch Again section of the festival website after about the 20th of June. And you're going to get an email when the video is available to view. So you can watch it again if you didn't get enough of the infinities. Thank you again for joining us. It's been great fun doing this. We might see you again at the festival next year. But otherwise, say goodnight, Emily.
See you later.
See you all later. Bye-bye.